There's something humbling about looking up at the night sky, something that connects us to every human who has ever lived. Picture this: thousands of years ago, before cities drowned out the stars with light, before telescopes or satellites, people stood beneath that same endless darkness, utterly transfixed. But they weren't just staring in awe. They were solving puzzles, piecing together patterns, asking questions that would change everything. The first astronomers didn't just watch the heavens, they listened to them. And what they heard rewired the human mind forever. Think about the sheer courage it took to turn your gaze upward and demand answers from the cosmos. These early stargazers had no textbooks, no calculators, no way of knowing whether the movements of the stars were random or meaningful. Yet, with nothing but patience and curiosity, they mapped the rhythms of the sky, predicting seasons, tracking time, even foreseeing eclipses. Their discoveries didn't just help them plant crops or navigate oceans. They sparked a revolution in how we see our place in the universe. Suddenly, the world wasn't just a chaotic swirl of events. It had order, predictability, a hidden logic waiting to be uncovered. This is the story of how the sky changed us. It's not just about constellations or ancient observatories. It's about the moment humanity realized the cosmos could be understood. That realization didn't just give us astronomy, it gave us science itself, philosophy, mathematics, even the way we measure time. All of them trace back to those first daring minds who dared to decode the night. So join me on a journey across millennia, where we'll meet the visionaries who turned starlight into knowledge and explore how their legacy still shapes the way we think today. Because when you look up tonight, you're not just seeing stars, you're seeing the birth of human curiosity written across the sky. Long before the first cities rose from the earth, before writing or wheels, human eyes were already locked onto the heavens. Imagine standing on an open plain 30,000 years ago, no streetlights, no screens, just the infinite theater of the night unfolding above you. The stars weren't just pretty lights back then. They were survival tools, calendars, and compasses woven into the fabric of daily life. When the Pleiades cluster appeared at dusk, it signaled time to plant. When Orion's belt tilted a certain way, it warned of coming storms. These patterns became humanity's first instruction manual, written in constellations. But the real breakthrough came when early cultures noticed something astonishing. The sky wasn't random. The moon cycled through phases with perfect regularity. The sun rose and set along predictable paths, shifting slightly each season like a slow, celestial dance. For hunter-gatherers living at nature's mercy, this reliability was revolutionary. Suddenly, the terrifying chaos of floods, droughts, and freezing winters had counterpoints in the steadfast rhythms above. The sky became a sacred clock, and learning to read it meant gaining power over time itself. Some of the oldest surviving structures on Earth tell this story. Take Newgrange in Ireland, a 5,000-year-old tomb designed so sunlight pierces its inner chamber only on the winter solstice, the shortest day of the year. Or the Babylonian star catalogues, meticulous clay tablets recording planetary movements centuries before telescopes existed. These weren't just practical tools, they were declarations of a profound idea. The universe followed rules, and humans could learn them. What's truly remarkable is how these celestial observations birthed abstract thought. Tracking the moon's cycles required counting. Predicting eclipses demanded geometry. The sky didn't just teach people when to sow crops, it taught them to think in sequences, patterns, and cause and effect relationships. In a very real sense, mathematics and science were born under those ancient stars. Every time you check a calendar or glance at a clock, you're using knowledge first written in the night sky by ancestors who dared to look up and wonder. This cosmic curiosity left its mark on culture too. Myths from Egypt to Mesoamerica wove stars into their creation stories, blending astronomy with spirituality. The Egyptians aligned pyramids with the North Star, believing pharaohs would join the gods in the heavens. The Maya developed a calendar so precise it could predict eclipses 1,000 years in advance. These weren't primitive superstitions, they were sophisticated attempts to reconcile human existence with the vast, ordered cosmos. When early astronomers charted Venus's path or measured solstice shadows, they weren't just studying the sky. They were laying the foundation for every scientific breakthrough that followed. Stonehenge rises from the English countryside like a question carved in stone. This ring of massive pillars, dragged over miles and painstakingly erected over generations, wasn't built for shelter or defense. It was designed to converse with the sky. Every summer solstice, the rising sun aligns perfectly with the heel stone, flooding the center of the circle with light. In winter, the setting sun slips between the towering arches with mathematical precision. These aren't coincidences, they're proof that 4,000 years ago, people were engineering monuments to mirror the cosmos. What's truly astonishing isn't just the accuracy of these alignments, but the sheer effort behind them. Without metal tools or wheels, Neolithic builders transported bluestones weighing up to 4 tons from quarries nearly 200 miles away. They shaped them using nothing but stone hammers and brute persistence. Why go to such extremes? Because to them, the movements of the sun and moon weren't just celestial events. They were sacred dialogues. Stonehenge may have been a temple where the heavens touched the earth, where priests decoded messages from the gods written in sunlight and shadow. Some researchers believe it functioned as a colossal calendar, its pillars acting as markers for eclipses and seasonal changes. Others argue it was a place of healing where the stones channeled cosmic energy. But perhaps the most compelling theory is that Stonehenge was a bridge between worlds. The arrangement of its stones creates acoustic effects, echoes that seem to ripple through time itself. When you stand in the center and speak, your voice resonates unnaturally, as if the monument amplifies more than sound. It's easy to imagine ancient ceremonies here, where chants to the sky gods mingled with the whispers of ancestors. What makes Stonehenge special isn't just its astronomical genius, but what it reveals about early human ambition. These builders didn't merely observe the cosmos, they sought to capture its rhythms in stone to make the intangible permanent. In an age before written language, they etched their understanding of time and space into the landscape itself. From Egypt's pyramids to Cambodia's Angkor Wat, this impulse to architecturally mirror the heavens would echo across civilizations. But Stonehenge came first, a silent, steadfast monument to humanity's first cosmic awe. When dawn light spills through those ancient stones today, it doesn't just illuminate grass. It illuminates the moment we began building our dreams into the fabric of the universe. While Stonehenge's stones whispered to the sun and moon, another civilization was turning astronomy into something revolutionary, a science of numbers. The Babylonians didn't just watch the stars, they measured them with a precision that still takes our breath away. Picture the bustling cities of Mesopotamia, where scribes pressed wedge-shaped marks into wet clay, not to record kings or battles, but to track the exact path of Venus across the night sky. These tablets, baked hard under the desert sun, became humanity's first scientific archives. What set the Babylonians apart was their obsession with patterns. They noticed that celestial events repeated in cycles, 8 years for Venus, 18 for the moon's wobbles, even 60 for certain planetary alignments. But here's the genius: they didn't just note these rhythms, they turned them into mathematics. Using a base 60 numbering system, while we still divide hours into 60 minutes today, they calculated planetary positions with startling accuracy. One tablet from around 300 BC predicts a solar eclipse to within minutes. Without telescopes or computers, they'd cracked the code of cosmic timing. Their secret weapon, early trigonometry. By charting the angles between stars, they could map the sky's geometry like surveyors measuring land. This wasn't stargazing for farming or religion. It was pure, abstract problem solving. The famous Plimpton 322 tablet, for instance, contains Pythagorean triples centuries before Pythagoras was born. Some historians argue the Babylonians even understood principles of calculus long before Newton. Yet their greatest legacy might be how they democratized the cosmos. While Egyptian priests guarded astronomical knowledge as sacred, Babylonian scribes treated it like public data. Schools taught astronomy alongside accounting, and merchants used star charts to time trade routes. The zodiac, a Babylonian invention dividing the sky into 12 equal slices to track the sun's yearly journey. Even their myths reflected this analytical mindset. Where others saw gods riding chariots across the heavens, Babylonians saw equations in motion. The irony is delicious. Today, we associate astrology with mysticism, but its Babylonian roots were rigorously mathematical. Their omen tablets often read like scientific reports. If Jupiter's position in such and such constellation, then barley prices will likely rise. For them, the sky wasn't just a divine message board, it was a cosmic clockwork where every gear turn had measurable consequences. When you check your watch or glance at a horoscope, you're touching the edge of a system forged by clerks counting stars under clay lamplight 25 centuries ago. Their real magic wasn't divination, it was proving the universe could be quantified, one cuneiform number at a time. Egypt's night sky wasn't just a spectacle, it was a sacred script, written in constellations and celestial movements. To them, the heavens pulsed with divinity. The sun god Ra didn't merely rise and set, he embarked on a perilous journey each day, battling the serpent of chaos, Apep, to ensure the world's survival. Stars weren't distant specks of light, they were the souls of the dead, glittering in the Jewat, the realm of the afterlife. This wasn't mere storytelling. It was a cosmological framework so precise that it shaped pyramids, guided agriculture, and even dictated the timing of religious festivals. Take the Great Pyramid of Giza. Its air shafts align with uncanny precision, one pointing directly to Orion's belt, another toward the North Star. These weren't architectural quirks. Orion, known as Sa to the Egyptians, represented Osiris, god of resurrection. The alignment mirrored their belief that pharaohs would join the gods in the stars, their souls ascending through these celestial corridors. But here's what's astonishing. Modern astronomers have confirmed these alignments would have been exact around 2500 BCE. That's no coincidence. It's evidence of meticulous observation passed down through generations of priest astronomers. Yet their cosmic vision went beyond symbolism. The Egyptian calendar, with its 3 seasons tied to the Nile's floods, was so accurate it only drifted by 1 day every 4 years, a feat the Gregorian calendar wouldn't match for millennia. Temple ceilings became star maps like the famous Dendera zodiac, depicting constellations with scientific detail. Even their myths held hidden astronomy lessons. The goddess Nut arched across the sky, swallowing the sun each evening and giving birth to it at dawn, encoded their understanding of the solar cycle. What's fascinating is how they balanced poetry with precision. While Babylonian astronomy focused on numbers, the Egyptians wrapped their cosmic knowledge in metaphor. The annual rising of Sirius, the dog star, signaled the Nile's life-giving floods, an event so vital it marked their new year, but they didn't just celebrate it as a divine gift. Records show they tracked Sirius's heliacal rising with such care that they noticed its slow drift over centuries, a phenomenon now known as axial precession. This fusion of myth and measurement reveals something profound about early science. For the Egyptians, studying the sky wasn't about separating religion from reality, it was about seeing them as one. When a priest observed the stars, he wasn't just collecting data, he was communing with the gods. Their temples doubled as observatories, their rituals as experiments. In a world where the sacred and the scientific were inseparable, the sky wasn't just a mystery to solve. It was a conversation with the divine, written in light and shadow, a dialogue that still echoes in the stones they left behind. The Greeks didn't just watch the stars, they argued about them. Picture the bustling agora of ancient Athens, where philosophers clashed over questions that would reshape human thought. Thales of Miletus, often called the first scientist, shocked his peers by predicting a solar eclipse in 585 BCE, not as an omen from the gods, but as a natural event following predictable laws. His student Anaximander went further, proposing Earth floated unsupported in space, with celestial bodies not riding divine chariots but moving in vast, invisible rings. These weren't just new ideas, they were intellectual earthquakes, shaking the very foundations of how humanity understood the cosmos. What made Greek astronomy revolutionary was its rejection of supernatural explanations. Where Babylonians saw omens and Egyptians saw gods, thinkers like Pythagoras saw geometry in motion. To him, the universe wasn't just orderly, it was musical. The planets moved in ratios so perfect they created a harmony of the spheres, an inaudible celestial symphony. His followers discovered Earth was round not by sailing around it, but by noticing its curved shadow on the moon during eclipses. This marriage of mathematics and observation birthed a radical concept: the universe operated by rules humans could decipher through reason alone. Yet the greatest legacy came from Aristotle, whose geocentric model placed Earth at the center of nested crystalline spheres. While we now know it's wrong, his system was a staggering achievement, the first complete, logical framework explaining planetary motions. He catalogued over 1,000 stars, distinguished planets from fixed stars by their wandering paths, and even correctly theorized the moon reflected sunlight. His mistake wasn't laziness, it was overconfidence in human senses. To Aristotle, if Earth felt stationary, it must be. The real breakthrough lay in their methods. Greek philosophers didn't just collect data, they debated it. Heraclitus insisted change was the only constant, while Parmenides argued reality was unchanging. This tension between observation and theory became science's beating heart. When Aristarchus proposed a heliocentric model 17 centuries before Copernicus, it wasn't rejected because of religion, but because it contradicted Aristotle's physics. Yet that very debate kept the idea alive, a spark waiting to ignite the scientific revolution. These thinkers gave us more than theories, they gave us the tools to question them. The word planet comes from their term for wanderer. Their word cosmos meant both universe and orderly beauty. In their hands, astronomy stopped being about predicting harvests or pleasing gods. It became a quest to understand reality itself. Every modern telescope, every space probe, every equation describing black holes owes a debt to those argumentative Greeks who looked up and dared to ask why instead of who. Their greatest gift wasn't answers, it was the courage to keep questioning. Claudius Ptolemy sat in the great library of Alexandria, surrounded by scrolls containing centuries of celestial observations. His task wasn't just to study the stars, it was to tame them. The result was the Almagest, a 13-volume masterpiece that became astronomy's first true textbook. Imagine the audacity of this project, to take everything humanity knew about the heavens' Babylonian star charts, Greek geometric models, Egyptian timetables, and weave them into a single, coherent system. Ptolemy didn't just record knowledge, he engineered a cosmic machine with gears of mathematics turning the planets in perfect, predictable circles. His geocentric model was wrong, of course. We know now that Earth isn't the universe's immovable center, but here's what's astonishing: Ptolemy's math worked. Using epicycles, those tiny circles planets traced while orbiting Earth, he could predict planetary positions with remarkable accuracy. When Mars appeared to loop backward in the night sky, a quirk we now know comes from Earth overtaking it in orbit. Ptolemy's equations accounted for it. His equant point, an off-center pivot that made planetary speeds vary, wasn't just a fudge factor. It was a stroke of computational genius that kept his model functional for over 1,400 years. The Almagest's real power lay in its completeness. It wasn't a collection of scattered theories, but a unified framework with step-by-step instructions. Want to calculate Venus's position next Tuesday? Ptolemy gave you the tools. Need to predict a lunar eclipse? The formulas were there. This practicality made it indispensable. Medieval Arab astronomers called it Al-Majesti, the greatest, while Renaissance scholars treated it like Holy Writ. Even Copernicus, who ultimately dismantled Ptolemy's system, studied the Almagest religiously, scribbling notes in its margins. What's often overlooked is how Ptolemy's work revealed a deeper truth about science. His errors weren't failures of imagination but limitations of perspective. With no telescopes or space probes, assuming Earth stood still was reasonable. Yet within those constraints, he pushed observation and mathematics further than anyone before him. The Almagest proved that imperfect models can still illuminate reality if they're precise enough to be tested, detailed enough to be improved. Every correction made by later astronomers, from Kepler's ellipses to Newton's gravity, stood on Ptolemy's shoulders. There's a poignant lesson here. We mock his epicycles now, those celestial doodles trying to force circles onto nature's ellipses. But Ptolemy's real legacy isn't his mistakes, it's his method. He showed that the universe could be described mathematically, that its secrets yielded to patient measurement and relentless logic. When Tycho Brahe's supernova shattered the idea of unchanging heavens in 1572, when Galileo's telescope revealed moons orbiting Jupiter, they weren't destroying Ptolemy's achievement. They were fulfilling it, proving that even wrong answers can lead to better questions. The Almagest didn't just map the stars, it mapped the human mind's capacity to reach for them. Deep in the jungles of Central America, where howler monkeys swung through the canopy and jaguars prowled the undergrowth, a civilization turned the night sky into a celestial spreadsheet. The Maya didn't just observe Venus, they stalked it like prey, tracking its movements with a precision that would make modern astronomers nod in respect. At El Caracol, a tower-like observatory in Chichen Itza with narrow windows perfectly aligned to Venus's extreme positions, priests recorded its cycles down to the hour. Their math was so advanced they calculated Venus's synodic period, the time it takes to return to the same point in the sky, as 584 days. Today's measurement, 583.92, that's a difference of less than 2 hours per century. What's truly mind-bending is how they wove this cosmic data into the fabric of daily life. The Dresden Codex, a bark paper book that survived Spanish conquest, contains pages of Venus tables predicting its positions over decades. But these weren't academic exercises. When Venus appeared as the morning star, it signaled time to plant corn. When it vanished behind the sun, kings launched wars, believing the planet's death and rebirth mirrored the cycle of conquest. The Maya didn't separate astronomy from destiny. They saw the sky as a divine battlefield where gods waged eternal wars, and earthly events were mere echoes. Their long count calendar, often reduced to that doomsday prediction, was actually a masterpiece of timekeeping. While Europeans still debated whether the year had 360 or 365 days, Maya astronomers had already accounted for the extra quarter day by adding adjustments like our leap year, but more precise. Their system could pinpoint dates millions of years in the past or future with perfect accuracy. The famous end date of 2012 wasn't an apocalyptic prophecy but a calendar reset, like a cosmic odometer rolling over. The real magic lay in their synthesis of observation and mythology. The Pleiades weren't just a star cluster, they were the rattles of a celestial serpent. Eclipses were cosmic jaguars devouring the sun, yet beneath the poetry was cold, hard calculation. At Capon, staircases are inscribed with numbers recording millions of days of astronomical history. Palin's Temple of the Inscriptions encodes the birth of a king within a Venus cycle. This wasn't superstition, it was a civilization so attuned to celestial rhythms that they built their identity around them. When a Maya noble gazed at the stars, he wasn't just seeing lights. He was reading a divine blueprint where politics, agriculture, and even personal fate moved to the clockwork of the cosmos. What makes the Maya unique is how they balanced brutal realism with celestial wonder. Their observatories doubled as temples because to them, measurement was worship. A king's legitimacy depended on his ability to predict eclipses, proving his connection to the gods. When Spanish friars burned their books as heresy, they weren't just destroying pagan nonsense. They were erasing a scientific tradition that had matched Earth's rotation to the flutter of a butterfly's wings. Today, as archaeologists decode more glyphs, we're realizing the Maya didn't just watch the sky. They wrote their history in it, etching human stories into the endless dance of planets and stars. While Europe's libraries crumbled and scientific inquiry dimmed during the so-called Dark Ages, a brilliant light burned steadily in the Islamic world. Cities like Baghdad, Damascus, and Cordoba became bustling hubs of scholarship where astronomers didn't just preserve ancient knowledge, they revolutionized it. Take al-Battani, working in 9th century Syria, who recalculated the length of the solar year with an error margin of just 2 minutes. His precise measurements of planetary orbits exposed flaws in Ptolemy's models, proving even the greatest theories could be refined. Then there was al-Sufi, whose Book of Fixed Stars didn't just copy Greek constellations, it corrected their positions and added new stars visible from the southern hemisphere, creating the most accurate celestial atlas of its time. What set these scholars apart wasn't just their meticulous observations, it was their tools. The astrolabe, perfected by Islamic craftsmen, became the medieval equivalent of a smartphone. This handheld brass computer could tell time, calculate prayer schedules, and even measure the height of mountains by aligning with the stars. Observatories like Maraghe in Persia featured quadrant walls the size of buildings, allowing astronomers to track planetary movements with unprecedented precision. While Europe still debated whether the Earth was round, scholars like Biruni used trigonometry to calculate its circumference within 200 miles of the correct value, and speculated centuries before Copernicus that Earth might orbit the Sun. Perhaps their greatest contribution was acting as humanity's memory keepers. When the famed House of Wisdom in Baghdad translated Greek texts into Arabic, they didn't just copy words, they interrogated them. Ptolemy's Almagest, Euclid's geometry, Aristotle's physics, all were scrutinized, annotated, and improved. Without these painstaking efforts, much of classical knowledge might have vanished during Europe's intellectual drought. When these works eventually reached the West through translations in Toledo and Sicily, they carried not just Greek wisdom but layers of Islamic commentary and correction. The scientific revolution didn't spring from nowhere. It stood on the shoulders of these unsung giants. Yet the most radical idea to emerge from this era wasn't a tool or a text, it was a method. Islamic astronomers treated the universe as a puzzle to be solved through math and observation, not dogma. When they noted discrepancies in Ptolemy's models, they didn't dismiss them as divine mysteries, they built new theories. Some, like Al-Haytham, even pioneered experimental techniques, insisting knowledge must be tested, not just inherited. This empirical approach would later echo in the works of Kepler and Galileo. The irony is profound. While medieval Europe often painted Islamic science as exotic or esoteric, its true legacy was relentless pragmatism. These scholars didn't separate faith from reason. They saw the study of creation as the highest form of worship. When you adjust your watch for daylight savings time, thank Al-Khwarizmi, whose algebra made such calculations possible. When you hear names like Betelgeuse and Vega, remember their Arabic words preserving centuries of star lore. The golden age of Islamic astronomy didn't just keep the lights on during humanity's intellectual night. It built the lanterns that would guide us into the modern world. Nicolaus Copernicus sat hunched over manuscripts in a quiet tower in Frombork, his quill scratching numbers that would unravel the universe. For 30 years, he refined his calculations in secret, knowing full well the firestorm they'd ignite. When, on the revolutions of the heavenly spheres, finally emerged in 1543, its opening line seemed harmless enough, dedicated to Pope Paul III, praising the majesty of celestial motions. But tucked inside was a bomb. Earth, he argued, was just another planet circling the sun, not the center, not special, a cosmic afterthought. The resistance wasn't just scholarly, it was existential. Ptolemy's Earth-centric model had anchored Western thought for 14 centuries. It wasn't merely a map of the skies, it was a map of meaning, placing humanity at the heart of creation. The Church had woven it into doctrine, poets into verse, philosophers into ethics. To challenge it wasn't just incorrect, it was sacrilege. Even Copernicus's allies balked. His student Rheticus had to publish the work anonymously, and the preface, likely added without consent, dismissed the theory as a mere mathematical convenience, not physical truth. Yet the real revolution wasn't in the math, it was in the mindset. Copernicus didn't have better telescopes than Ptolemy, he had a braver imagination. His models solved celestial quirks with elegant simplicity. Mars's looping retrograde motion, an illusion caused by Earth overtaking it in orbit, the sun's shifting speed across seasons. A consequence of our off-center orbit, suddenly, epicycles, those clunky circles Ptolemy used to force planets into Earth-centered paths, were obsolete. The universe made more sense if you stood on the sun and watched the planets dance around it. But here's what's fascinating. Copernicus wasn't some rebel shouting into the void. He was a cautious canon lawyer, terrified of ridicule. He delayed publishing until his deathbed, and his models still clung to circular orbits, needing minor tweaks to match observations. The real courage came from those who built on his work, like Galileo, who turned his telescope to Jupiter's moons and proved not everything orbited Earth, or Kepler, who replaced Copernicus's circles with ellipses, finally unlocking the planet's true path. The shockwaves of this idea reached far beyond astronomy. If Earth wasn't central, what else might humanity have wrong? Theologians grappled with a universe where Eden might be just another speck. Poets like John Donne lamented the new philosophy that put all in doubt. Yet this demotion birthed something profound: humility. No longer the universe's darlings, humans became its students, free to explore, question, and discover without the weight of cosmic privilege. Every modern space probe, every search for exoplanets, every wondering gaze at the stars owes a debt to that timid canon in Frombork who dared to scribble the truth. Tycho Brahe's island observatory, Uraniborg, wasn't just a workplace, it was a temple to precision. Perched on the Danish island of Ven, its walls bristled with custom-built instruments so massive they could measure star positions down to 1/60th of a degree. To put that in perspective, that's like spotting a coin from 2 miles away and pinpointing its exact location with your bare eyes. At a time when most astronomers still relied on Ptolemy's centuries-old data, Brahe spent 20 years methodically recording the night sky, night after night, without the aid of a single lens. His secret, a blend of obsessive detail and engineering genius. Take his great mural quadrant, a colossal brass arc spanning an entire room. By aligning its sites with specific stars, Brahe could track planetary movements with unprecedented accuracy. His records of Mars's path, particularly its puzzling retrograde loops, were so precise they deviated from existing models by 8 full degrees. That discrepancy would later haunt his assistant, Johannes Kepler, who realized only elliptical orbits could explain Brahe's stubborn data. Without those painstaking measurements, Kepler might never have shattered the ancient belief in perfect celestial circles. But Brahe's genius wasn't just in his instruments, it was in his methodology. He introduced the concept of daily calibration, checking his tools against reference stars to account for even the tiniest errors. He accounted for atmospheric refraction, that subtle bending of starlight as it passes through air, correcting for distortions no one else bothered to consider. When a supernova blazed into view in 1572, most scholars dismissed it as some atmospheric fluke. Brahe, though, meticulously documented its unchanging position, proving it lay far beyond the moon, a direct challenge to Aristotle's doctrine of an unchanging celestial realm. Then there's the man himself, whose life reads like a Renaissance soap opera. After losing his nose in a duel over a mathematical formula, yes, really, he wore a brass prosthetic reportedly stuffed with ointment to soothe the scar. His pet moose, a gift from the King of Sweden, allegedly died after drunkenly tumbling down castle stairs. Yet beneath the eccentricities lay a revolutionary ethos. The universe could be understood through relentless measurement. When Emperor Rudolf II lured him to Prague, Brahe arrived with 4 printing presses, not to publish books, but to mass-produce data tables for fellow scholars. What makes Brahe's legacy so enduring isn't just his data's accuracy, but his defiant spirit. In an age when astronomy still danced with astrology, he insisted on separating celestial mechanics from mystical interpretation. His famous Tychonic system, a hybrid where planets orbited the Sun while the Sun orbited Earth, may have been a diplomatic compromise, but its calculations were uncompromisingly empirical. When Kepler inherited his records after Brahe's sudden death, rumored to be from a burst bladder at a banquet, he didn't just get numbers, he inherited a manifesto. The heavens yield their secrets only to those who measure without mercy. That's why Brahe's Uraniborg, though long crumbled into the Baltic winds, still stands as a monument, not to answers but to questions, to the idea that progress begins when we admit our models are flawed and our instruments must be sharper. His real gift wasn't a map of the skies, but a challenge: measure again, look closer. The truth is out there, waiting for someone patient enough to count every flicker. Johannes Kepler stared at Tycho Brahe's mountain of planetary data like a detective confronting an unsolved cipher. The numbers didn't lie. Mars's orbit stubbornly refused to fit the perfect circles everyone from Aristotle to Copernicus had insisted must govern the heavens. Then came the flash of insight that would rewrite cosmic history. What if planets moved not in circles but ellipses? The realization hit him like a lightning strike. For centuries, humanity had worshipped geometric perfection, assuming the divine must favor symmetry. But Kepler's calculations revealed a deeper truth: the universe prized precision over prettiness. His first law shattered 2,000 years of dogma in one sentence. Planets orbit the sun in elliptical paths, with the sun not at the center, but at one focus point. This wasn't just a tweak to the model, it was a revolution in perspective. That subtle oval shape explained why planets speed up when closer to the sun and slow down when farther away, a phenomenon Kepler quantified in his second law. Picture a cosmic dance where each planet sweeps out equal areas in equal times, like a spinning ice skater pulling their arms in to rotate faster. No more clunky epicycles or fudged calculations. The math suddenly clicked because it mirrored reality, not idealism. Yet Kepler's masterstroke came with his third law, which tied a planet's orbital period to its distance from the sun with mathematical elegance. The farther a planet was, the longer its year, and not randomly but following an exact ratio. For the first time, the solar system wasn't just described, it was unified by a single equation. What's often overlooked is how deeply music shaped Kepler's thinking. He'd been obsessed since childhood with Pythagoras' idea of celestial harmonies, the notion that planets hummed as they moved, their pitches determined by orbital speeds. Though wrong in detail, this poetic vision guided him toward his laws. In his book, Harmonious Mundi, he assigned musical notes to planets based on their velocity extremes: Saturn a deep G, Earth a middle F sharp. The result, a haunting cosmic chord only the universe could hear. Modern scientists might smile at the whimsy, but Kepler's blend of poetry and precision captures something profound. Science isn't just about cold equations, it's about finding the melody hidden in the noise. Kepler's legacy isn't just 3 laws in a textbook. It's the moment astronomy grew up, when we stopped forcing nature into comfortable shapes and let the data speak. His work became the bridge between Brahe's meticulous observations and Newton's grand theory of gravity. Those elliptical orbits, once seen as imperfections, turned out to be signatures of a deeper order, one where even the slightest asymmetry holds the key to understanding everything. When Voyager spacecraft slingshot around planets using Kepler's math, or when astronomers pinpoint exoplanets by their starlight dips, they're following the trail blazed by a man who dared to believe the universe's song was worth deciphering one imperfect, beautiful ellipse at a time. Galileo's hands trembled as he adjusted the lens of his strange new instrument, a tube of lead and leather with glass at both ends. What he saw that night in 1609 would rewrite the cosmos. Jupiter wasn't alone. 4 tiny stars flanked it, shifting position nightly like obedient attendants. These weren't stars at all, they were moons circling another world. The implications struck him like a physical blow. If Jupiter had satellites that didn't orbit Earth, then Aristotle's perfect geocentric universe was fiction. The Church's insistence that everything revolved around humanity, shattered by 4 flickering dots of light. But Galileo didn't stop there. Turning his telescope to the moon, he found another heresy. Its surface wasn't a smooth, divine sphere as philosophers claimed. It was pockmarked with craters and scarred by mountains casting jagged shadows. The heavens, it seemed, were as flawed and textured as the Earth itself. Even the Milky Way dissolved under magnification into countless individual stars, proving the universe vaster than anyone dreamed. Each observation was a hammer blow to medieval cosmology, and Galileo knew it. He published his findings in Sidereus Nuncius, the Starry Messenger, a slim volume that ignited both scientific fervor and clerical fury. The backlash was swift. Fellow scholars refused to even look through his telescope, dismissing the moons of Jupiter as optical illusions. Church authorities grew uneasy as Galileo's evidence undermined scriptural interpretations of an Earth-centered universe. His growing fame and blunt defiance earned him powerful enemies. When he mocked those who clung to tradition in his dialogue concerning the two chief world systems, framing a straw-man character named Simplicio to voice papal arguments, the Inquisition had enough. In 1633, under threat of torture, the aging astronomer knelt to recant his errors. Legend claims he muttered under his breath, and yet it moves. What makes Galileo's story so pivotal isn't just his discoveries, it's his method. Where Kepler theorized with mathematics, Galileo proved truths through repeatable observation. His meticulous notes on Jupiter's moons could be verified by anyone with a decent telescope, turning personal insight into public knowledge. This shift from abstract philosophy to evidence-based science marks the birth of modern empiricism. The tools mattered as much as the ideas. By grinding his own lenses and refining his designs, Galileo demonstrated that technological innovation drives intellectual revolution. His defiance carried a cost. Spending his final years under house arrest, blind but still working, Galileo became science's first martyr to dogma. Yet his legacy outshone his persecutors. Those same Jesuit astronomers who condemned him later used his methods to map comets and refine calendars. The telescope, once deemed heretical, became astronomy's foundational tool. Most importantly, Galileo proved a radical idea, that truth isn't decreed by authorities but revealed through patient looking, testing, and daring to trust your own eyes. Every time a modern astronomer points a telescope skyward, they're standing on the shoulders of a man who refused to stop gazing, even when the world demanded he kneel. Isaac Newton's breakthrough didn't come in a lab or an observatory, it began in an orchard. The legendary apple might be folklore, but the insight was real. The same force pulling fruit to the ground must also tether the moon to Earth. For centuries, thinkers had assumed celestial and earthly physics were separate realms, planets gliding on crystalline spheres, while objects below obeyed crude, mundane laws. Newton's genius was to see the connection. In his monumental Philosophiae Naturalis Principia Mathematica, he didn't just describe gravity, he gave it a language. Mathematics, the heart of his revelation, was the inverse square law. The force between two objects weakens with the square of their distance. A planet twice as far from the Sun feels not half the pull, but 1/4. This simple relationship explained everything: why comets traced parabolic paths, why ocean tides synchronized with the moon, even why Earth bulged slightly at its equator. But Newton's gravity wasn't just about equations. It was a radical democratization of the cosmos. The same rules governed falling apples and orbiting Jupiter, making the universe astonishingly unified. What made the Principia revolutionary wasn't just its accuracy, it was its predictive power. When astronomers spotted irregularities in Uranus's orbit, Newton's laws pointed to an unseen planet tugging on it. The result, Neptune, discovered in 1846 through pure calculation. Halley's Comet, once a terrifying omen, became a predictable visitor thanks to Newton's clockwork cosmos. Even the moon's subtle wobbles, which had baffled observers for centuries, suddenly made sense as gravitational tugs from the sun. Yet Newton himself was haunted by the how. His laws described gravity's effects perfectly but couldn't explain its essence. How could the sun reach across 93 million miles of empty space to grip Earth? In his letters, he admitted this mystery kept him awake at night, calling the idea of invisible, instantaneous action so great an absurdity that I believe no man can ever fall into it. It would take Einstein to unravel that riddle centuries later. The true legacy of Newton's gravity lies in its humility. By insisting nature followed consistent laws rather than divine whims, he made the universe knowable. No longer did comets signal God's wrath or planets move by angelic hands. The heavens ran on principles anyone could test, with a telescope, a pendulum, or even an apple. When astronauts hurled a feather and hammer together on the moon, proving they fell at the same rate without air resistance, they weren't just doing a stunt. They were fulfilling Newton's vision, a cosmos where everything, from the smallest pebble to the grandest galaxy, dances to the same silent, irresistible tune. William Herschel's hands were calloused from years of grinding mirrors, but his eyes were sharper than any telescope. On that fateful night in 1781, sweeping the sky from his backyard in Bath, England, he spotted a faint disk where only a point of light should be. At first, he assumed it was a comet until its orbit revealed the unthinkable. This was no icy wanderer, but a new planet, the first discovered since antiquity. Uranus doubled the known size of the solar system overnight, but Herschel's real revolution wasn't in finding a world. It was in transforming how we see the universe itself. While most astronomers still viewed stars as static decorations on a celestial sphere, Herschel saw them as suns at different distances. With his sister Caroline tirelessly recording his observations, he conducted the first systematic star gauges, counting stars in hundreds of sky regions to map the Milky Way's shape. His conclusion: the heavens weren't a shallow dome but an incomprehensibly vast disk, with our solar system embedded inside like a speck of dust in a cosmic whirlpool. This was the birth of galactic astronomy, the realization that the Milky Way wasn't the entire universe, but merely one island of stars among countless others. Caroline Herschel's role in this revolution was nothing short of extraordinary. Initially hired as William's housekeeper, she became his indispensable partner, polishing mirrors, sweeping the sky with smaller telescopes, and discovering 8 comets in her own right. When King George III granted her a salary in 1796, she became the first woman officially recognized as a professional astronomer. Her meticulous catalogues of nebulae and star clusters laid groundwork for later explorers of the deep sky. Yet history often forgets her most vital contribution, keeping William's audacious ideas grounded in rigorous data. Without Caroline's precision, his grand theories might have drifted into speculation. The Herschel's greatest insight came from an unexpected tool: thermometers. By measuring the temperature difference between various colored stars, William stumbled upon infrared radiation, proving light existed beyond the visible spectrum. This accidental discovery mirrored their broader philosophy. The universe was alive with hidden processes. Stars weren't eternal fixtures but dynamic objects with life cycles, some newborn, others dying. Their observations of nebulae, later understood as stellar nurseries, suggested cosmic evolution long before Darwin applied the concept to biology. What makes their legacy so enduring is how profoundly human it remains. William's 40-foot telescope, the largest of its age, was a wooden behemoth that groaned in the wind like a ship's mast. Caroline's journals overflow with frustration at cloudy nights and ink frozen in winter. These weren't remote geniuses in ivory towers but passionate stargazers who hauled telescopes into gardens and burned fingers on polishing pitch. When William dubbed Uranus Georgium Sidus to flatter his patron, international astronomers rejected the name, a reminder that even revolutionary minds are products of their time. Their story transcends astronomy. In an era when women were barred from universities and science was a gentleman's hobby, The Herschel's proved discovery thrives on diversity of thought, background, and perspective. Every modern astrophoto of swirling galaxies, every detection of exoplanets orbiting distant suns, carries echoes of that backyard in Bath where a brother and sister redefined our place in the cosmos. They taught us to see the universe not as a static backdrop, but as a living, changing tapestry, one we're only beginning to unravel. Albert Einstein sat at his desk in the Swiss patent office, scribbling equations that would unravel the very fabric of reality. While Newton saw gravity as a mysterious force acting across space, Einstein envisioned something far more radical. Space and time weren't just a stage for the universe's drama. They were actors in it, bending and warping under the weight of matter. His general theory of relativity didn't merely tweak our understanding of gravity, it rewrote the script entirely. Picture the cosmos as a trampoline, with planets and stars creating dimples in its surface. A marble rolling near one of these curves doesn't fall because of some invisible tug. It follows the natural slope of warped space. Gravity, Einstein realized, wasn't a force at all. It was geometry. The implications were staggering. If mass could bend space, then light, long thought to travel in unwavering straight lines, must follow those curves too. During the solar eclipse of 1919, astronomers proved Einstein right by photographing starlight bending around the sun, exactly as his equations predicted. But the strangest predictions lay hidden in the math. Time itself flowed slower near massive objects. A clock at sea level, closer to Earth's gravitational pull, ticks more sluggishly than one atop a mountain. GPS satellites orbiting high above our planet have to account for this time warp, adjusting their signals by milliseconds to keep navigation systems accurate. The universe, it seemed, was a far more malleable place than anyone had dared imagine. Then came the most mind-bending consequence of all, black holes. Einstein's equations suggested that if enough mass crammed into a small enough space, it could warp space-time so severely that not even light could escape. At first, even Einstein dismissed the idea as too fantastical. But by the 1960s, astronomers were spotting telltale X-rays from invisible objects with the mass of stars, their gravitational grip twisting nearby matter into glowing disks. The first direct image of a black hole's shadow in 2019, a fiery ring surrounding darkness, was the ultimate validation of relativity's power. Yet perhaps Einstein's greatest legacy wasn't just in the celestial extremes, it was in the everyday. His theory revealed that the universe wasn't a collection of isolated objects governed by rigid laws, but a dynamic tapestry where matter and space-time dance together. When two black holes collide, they send ripples through this cosmic fabric. Gravitational waves detected a century after Einstein predicted them. These faint tremors, captured by lasers in facilities like LIGO, remind us that space isn't empty stillness. It's a living, breathing entity, stretching and compressing like the surface of a vast, invisible ocean. The beauty of relativity lies in its paradoxes. It tells us the laws of physics are absolute, yet time and space are fluid. It describes a universe of breathtaking order, where equations predict black holes with pinpoint accuracy, yet one where reality itself twists like a funhouse mirror near a neutron star. Einstein didn't just give us new answers, he taught us to ask better questions. Every time your phone's GPS adjusts for time dilation, or astronomers map dark matter by how it bends light, they're not just using his theory. They're stepping into the warped, wondrous universe he first glimpsed in a patent office, where the simplest truths hide in the curves of spacetime itself. Edwin Hubble peered through the 100-inch Hooker telescope at Mount Wilson, his eyes tracing the faint smudges of light that littered the night sky. These weren't just distant stars, they were entire galaxies, islands of billions of suns floating in the void. But what stunned Hubble wasn't their existence, it was their behavior. By measuring the redshift of their light, he noticed something extraordinary. Nearly every galaxy was hurtling away from us, their light stretched into longer, redder wavelengths like the fading whistle of a departing train. The farther away a galaxy was, the faster it raced into the distance. The universe wasn't just vast, it was stretching, expanding in all directions like a cosmic loaf of bread rising in the oven. This revelation turned centuries of astronomy on its head. Until Hubble's discovery in the 1920s, most scientists assumed the universe was static, a fixed backdrop where stars and galaxies drifted but never fundamentally changed. Even Einstein had tweaked his equations of general relativity to preserve this idea, adding a cosmological constant to prevent the universe from collapsing or expanding. When Hubble's data proved otherwise, Einstein reportedly called this adjustment his greatest blunder. But the real shock wasn't just that space was growing, it was what this implied about the past. If galaxies were racing apart now, they must have been closer together yesterday. Rewind the tape far enough, and everything in existence would converge to a single, unimaginably dense point. The Big Bang Theory wasn't just a hypothesis anymore. It was the inescapable conclusion written in the light of fleeing galaxies. Hubble's breakthrough came from a brilliant marriage of observation and interpretation. He didn't just collect data, he connected dots across disciplines. By correlating galactic distances measured using Cepheid variable stars as cosmic yardsticks with their redshifts, he uncovered a linear relationship now called Hubble's law. The slope of that line revealed the universe's expansion rate, a number so pivotal it's known simply as the Hubble constant. Modern satellites like Gaia and Hubble's namesake telescope have refined this value, but the core insight remains. Space itself is stretching, carrying galaxies along like raisins in rising dough. What makes this discovery so profound is how it reshaped humanity's place in the cosmos. No longer were we passive observers of an eternal, unchanging sky. We were witnesses to a dynamic universe with a beginning, a middle, and perhaps an end. The realization that galaxies rush away not through space but with space, that the vacuum between stars isn't empty but actively growing, shattered old metaphors. Even the Milky Way wasn't special. It was just one of countless galaxies adrift in an ever-widening sea of darkness. Yet Hubble's legacy isn't just in the equations. It's in the questions his work forced us to confront. If the universe is expanding, what's driving it? Dark energy, some mysterious property of space itself? And what came before the Big Bang? These puzzles now define modern cosmology, proving that every answer unlocks deeper mysteries. When you gaze at the Hubble Deep Field, that iconic image of thousands of galaxies crammed into a patch of sky no bigger than a grain of sand held at arm's length, you're not just seeing distant suns. You're seeing the aftermath of a cosmic explosion, the scattered embers of a fire that ignited everything we know. And somewhere in that glow, Edwin Hubble's lesson still holds. The universe isn't just out there, it's happening. Carl Jansky never set out to revolutionize astronomy. He was just trying to solve a phone company's static problem. Perched atop a New Jersey field in 1931, his ungainly contraption of brass pipes and wooden boards looked more like a backyard experiment than a scientific breakthrough. But when his rotating antenna kept picking up a mysterious hiss that rose and fell every 23 hours and 56 minutes, Jansky realized something extraordinary. This wasn't electrical interference, it was the Milky Way itself, singing to Earth in crackles of radio waves. For millennia, humanity had studied the cosmos through the narrow window of visible light. But Jansky's accidental discovery flung open an entirely new shutter. Suddenly, astronomers could hear the universe through thick clouds of interstellar dust that had blocked optical telescopes for centuries. The first radio sky maps revealed a cosmos far stranger than anyone imagined: pulsars blinking like cosmic lighthouses, quasars beaming energy from the edge of time, even the faint whisper of radiation left over from the Big Bang itself. Where optical astronomy showed stars as pinpricks of light, radio telescopes revealed their hidden lives: the death throes of supernova, the swirling dance of particles around black holes, the birth cries of new solar systems. The real power of radio astronomy lies in its ability to uncover the invisible. Take the discovery of pulsars in 1967, when Jocelyn Bell Burnell noticed a regular tick in her radio telescope data, so precise it was initially nicknamed LGM for Little Green Men. She'd stumbled upon rapidly spinning neutron stars, the densest objects in the universe besides black holes. These cosmic timekeepers pulse with such regularity that they've been used to test Einstein's theory of relativity, their rhythms distorted ever so slightly by gravitational waves passing through spacetime. Then there's the cosmic microwave background, the afterglow of the Big Bang, first detected by Penzias and Wilson in 1965. That faint static filling every radio telescope isn't noise, it's the cooled remnant of the universe's fiery birth, stretched from visible light into microwaves over 13 billion years. By mapping its tiny fluctuations, cosmologists have reconstructed the infant universe's structure like paleontologists deciphering fossils. What makes radio astronomy so transformative is how it complements, and sometimes contradicts, optical observations. When astronomers first tracked radio emissions from the center of our galaxy, they expected to find a supermassive black hole, but no visible object matched the radio source's position until decades later, when infrared telescopes finally pierced the dust to reveal Sagittarius, a star, a black hole 4 million times the Sun's mass. Radio waves had told the truth long before light could confirm it. Today's vast radio arrays, like the Atacama Large Millimeter Array in Chile or the upcoming Square Kilometer Array across 2 continents, aren't just bigger versions of Jansky's spinning antenna. They're time machines capturing signals emitted billions of years ago from galaxies now vanished. They're forensic tools tracing the distribution of molecules that might seed life around young stars. And they're universal translators, decoding a cosmos that speaks in wavelengths far beyond what our eyes can see. Every time your car radio crackles with static between stations, remember, you're hearing the faintest echoes of a conversation that began with the birth of the universe itself. The beep, beep, beep of Sputnik in 1957 didn't just echo across radio frequencies, it shattered an ancient barrier. For the first time in human history, our instruments weren't confined to Earth's surface, straining against the blur of atmosphere. They were up there, floating in the void itself. That crude metal sphere, no bigger than a beach ball, marked the moment astronomy left its cradle. Suddenly, the stars weren't just points of light to observe, they were destinations. What followed was an explosion of cosmic reconnaissance. The Mariner probes raced to Venus and Mars, their grainy black and white images revealing cratered landscapes where writers had once imagined canals and jungles. Viking's robotic arms scooped up Martian soil, searching for microbes in what was now unmistakably a desert world. But the real game changer came with Voyager, those twin explorers flung toward the outer planets like messages in bottles. When Voyager 1 turned its camera homeward in 1990, capturing Earth as a pale blue dot from 4 billion miles away, it didn't just send a photo. It delivered a revelation: we were inconceivably small, floating in a vast and indifferent cosmos. Then there was Hubble, our first permanent eye above the atmosphere. Named for the astronomer who proved galaxies existed beyond our own, this orbiting observatory transformed fuzzy smudges of light into swirling stellar nurseries and colliding galaxies. Without air to scatter its view, Hubble could peer deeper into space and further back in time than any ground-based telescope. Its ultra-deep field image, created by staring at an empty patch of sky for 11 days, revealed thousands of galaxies in a space no wider than a grain of sand held at arm's length. Each speck of light represented billions of stars, each potentially hosting planets, maybe even life. The universe had grown exponentially larger in our imagination, thanks to a telescope that never blinked. The space age didn't just expand our knowledge, it rewrote the questions. When Cassini plunged into Saturn's atmosphere after 13 years of discovery, it wasn't just the end of a mission. It was the closing of a chapter where we'd learned that moons like Enceladus had subsurface oceans, that Titan's methane lakes mirrored Earth's water cycle. These weren't dead rocks circling a gas giant. They were worlds with their own stories, their own possibilities. Now, as probes like Juno map Jupiter's storms and Perseverance drills into Martian rocks, we're no longer just observers of the cosmos. We're participants, sending mechanical ambassadors across the solar system and beyond. Voyager's golden records, carrying greetings in 55 languages, drift toward interstellar space, a message to whoever might find them that once, on a tiny rock near an ordinary star, a species looked up and dared to reach beyond its cradle. The space age didn't just change how we see the universe, it changed how the universe might one day see us. Vera Rubin peered at the whirling stars of the Andromeda galaxy through her telescope, expecting to see a familiar cosmic dance. According to Newton's laws, stars on the outer edges of a galaxy should move slower than those near the center like planets in our solar system, with Mercury zipping around the Sun while Pluto crawls. But the data told a different story. No matter how far out Rubin measured, stars raced at nearly the same breakneck speed, as if some invisible hand kept them from flying into the void. The numbers didn't lie. Galaxies were spinning so fast they should have torn themselves apart, unless Rubin realized something unseen was holding them together, something massive, mysterious, and utterly dark. This wasn't just a minor discrepancy. Rubin's work in the 1970s exposed a gaping hole in our understanding of the universe. The visible stars and gas in galaxies accounted for barely 10% of the gravity needed to explain their motion. The rest, over 90% of the universe's matter, wasn't just hidden. It was something entirely foreign, a substance that didn't absorb, reflect, or emit light. Astronomers called it dark matter, and its discovery turned cosmology upside down. Suddenly, everything we could see, every galaxy, every nebula, every star, was just the glittering tip of an invisible iceberg. The hunt for dark matter's identity became science's greatest detective story. Some theorists proposed WIMP, weakly interacting massive particles, hypothetical subatomic entities that barely interact with normal matter except through gravity. Others suggested actions, ultra-light particles born in the early universe. Experiments like the Large Hadron Collider smashed protons together at near light speeds, hoping to create dark matter in the debris. Deep underground, detectors filled with liquid xenon waited for the faintest shudder of a dark particle passing through. Yet decades later, the mystery persists. Dark matter remains stubbornly invisible, revealing itself only through the gravitational grip it exerts on galaxies and the way it bends light like a cosmic magnifying glass. What makes dark matter so thrilling isn't just its elusiveness, it's the way it reshapes our cosmic map. When astronomers traced the large-scale structure of the universe, they found galaxies clustered along vast, tangled filaments like foam on an invisible ocean. Computer simulations showed this cosmic web couldn't form without dark matter's gravitational scaffolding. Without it, stars would never have clumped into galaxies, and galaxies never into clusters. We owe our existence to this unseen architect, yet the most humbling lesson of dark matter is how little we truly know. For all our telescopes and equations, 85% of the universe's matter remains unknown. It's a reminder that the cosmos is far stranger than our theories dare to imagine. Every time astronomers map a new galaxy's rotation or measure the warp of space-time around a cluster, they're not just collecting data, they're eavesdropping on a conversation between the visible and the invisible, a dialogue written in gravity's silent language. And somewhere in that darkness, the universe keeps its oldest secrets. The night sky used to be a gallery of stars, fixed, distant, untouchable. Then came October 6, 1995, when astronomers Mitchell Mayer and Didier Queloz pointed their telescope toward a sun-like star 50 light-years away and found something impossible. A planet half the mass of Jupiter whirling around its star in just 4 days. 51 Pegasi b shouldn't have existed. According to prevailing theories, gas giants needed wide orbits to form, yet here one was practically skimming its star's surface like a moth drawn too close to a flame. Overnight, the cosmic rulebook burned to ash. If planets could thrive in places science said they shouldn't, then the universe was far wilder than we'd dared to dream. Fast forward 3 decades, and the exoplanet gold rush has rewritten astronomy's atlas. Kepler, TESS, and other planet-hunting telescopes have turned up over 5,000 confirmed worlds, some boiling under twin suns, others drifting alone in eternal night, a handful eerily Earth-like. The methods themselves read like science fiction. There's the wobble technique, catching stars tugged by invisible planets like a dancer pulled off balance by an unseen partner. The transit method, spotting microscopic dips in starlight as planets cross their sun's faces like detecting a moth passing in front of a searchlight from 1,000 miles away. And now, direct imaging, where coronagraphs block a star's glare to reveal faint planetary specks, like picking out a firefly beside a bonfire. But the real magic lies in the outliers. Take HD 189733b, a cobalt blue gas giant where it rains molten glass sideways in 1,000-mile-per-hour winds, or TOI 700d, a rocky world bathed in eternal twilight, where tidal locking means one side always faces its star while the other freezes in darkness, yet somewhere in between might lie a sliver of habitable twilight. Then there's the TRAPPIST-1 system, 7 Earth-sized worlds packed closer than Mercury's orbit, their years shorter than our weeks. If you stood on one, neighboring planets would loom in the sky like ghostly marbles, close enough to see continents and clouds. These discoveries aren't just expanding our catalogue of worlds, they're forcing us to redefine life itself. Astrobiologists now speak of shadow biospheres, organisms built from silicon instead of carbon, thriving in ammonia lakes or beneath ice shields. They debate whether tidally locked planets could host life in their terminator zones, where day meets night in a perpetual sunset. Every strange new world chips away at Earth's status as the Goldilocks exception. If life can spark in Jupiter's acidic clouds or Saturn's frigid moons, why not on some distant super-Earth with skies choked by nitrogen? Yet the deepest impact isn't scientific, it's existential. For centuries, philosophers asked if we were alone. Now we know the cosmos teems with planets, and statistics suggest billions could harbor liquid water. The silence of the universe, the eerie lack of alien signals known as the Fermi paradox, grows louder with each discovery. Are we rare early, or is something more ominous at play? The search for exoplanets has become a mirror, reflecting back our hopes and fears about humanity's place in the cosmos. every time a new world blips onto our screens, it doesn't just answer a question. It asks a deeper one. If the universe is so crowded, why does it feel so empty? And what happens to human ambition when we finally find our reflection in the stars? Black holes began as ghosts in the equations, mathematical phantoms so bizarre even Einstein doubted they could exist. When Karl Schwarzschild solved Einstein's field equations in 1916, revealing the possibility of infinitely dense points where spacetime curvature became infinite, most physicists shrugged it off as a theoretical curiosity. After all, nature abhors infinities, but the universe, it turns out, has a flair for the dramatic. Fast forward a century, and we've not only proven black holes are real, we've photographed one. The now iconic image of the supermassive black hole at the heart of galaxy M87, released in 2019, didn't just validate relativity with poetic precision. It gave humanity its first glimpse of the universe's most perfect paradox, a shadow ringed by fire, where gravity's grip is so absolute that the very concept of here and now ceases to have meaning. What makes black holes so mesmerizing isn't just their destructive power, it's how they warp reality itself. Picture spacetime as a stretched rubber sheet. Place a bowling ball on it, and it creates a depression. That's how stars and planets curve space. But a black hole is like a needle punching clean through the fabric, creating a hole so deep that anything crossing its edge, the event horizon, can never climb back out. Even light, the fastest thing in the universe, becomes trapped in this gravitational quicksand. The M87 image captures this beautifully, a dark void encircled by a swirling disk of superheated gas, its photons twisted into a fiery halo by gravitational lensing. That glowing ring isn't just plasma, it's the last desperate cry of light itself, bent into a perfect circle by spacetime's curvature before vanishing into oblivion. Yet black holes aren't just cosmic vacuum cleaners, they're laboratories for physics at its most extreme. At their cores lies the singularity, a point where density becomes infinite and the laws of physics as we know them break down. Here, quantum mechanics and general relativity, the twin pillars of modern physics, collide in a battle neither can win. Some theorists propose that singularities might be gateways to other universes or tunnels through spacetime wormholes. Others suggest they could be holograms, with all the information about what falls in encoded on their surfaces like a cosmic thumb drive. The black hole information paradox, debating whether matter swallowed by a black hole is truly destroyed, violating quantum mechanics, or preserved mocking relativity, remains one of science's fiercest debates. The discovery that nearly every galaxy harbors a supermassive black hole at its center, including our own Milky Way's 4 million solar mass behemoth, Sagittarius a star, has rewritten galactic evolution. Far from being mere destroyers, these monsters may be cosmic sculptors. When they feed on gas and stars, the resulting energy outbursts can quench star formation across entire galaxies, effectively setting their lifespan. Some astronomers speculate that black holes and galaxies grow in lockstep, a cosmic symbiosis we're only beginning to understand. Even stranger are the rogue black holes drifting between galaxies, ejected by gravitational interactions, dark nomads wandering the cosmic void. Perhaps the most humbling lesson black holes teach is how much we still don't know. The Event Horizon Telescope's next target, Sagittarius, a star itself, could reveal how black holes flicker and flare as they consume matter. Gravitational wave detectors like LIGO listen for the ripples from colliding black holes, each merger a thunderclap in the fabric of space-time. And as we peer deeper, we're forced to confront a universe far stranger than Einstein ever imagined, one where the darkest objects hold the brightest secrets, and the abyss isn't just empty space, but a mirror reflecting the limits of human knowledge. The James Webb Space Telescope unfolded its golden mirrors like a cosmic origami masterpiece, each hexagonal segment aligning with nanometer precision to capture light that had traveled for over 13 billion years. Unlike Hubble's visible light snapshots, Webb's infrared eyes pierce through cosmic dust and redshift, revealing the universe's baby photos galaxies sparkling into existence when the cosmos was a mere 5% of its current age. One of its first targets, the galaxy cluster SMACS 0723, became a gravitational lens magnifying even more distant objects behind it, like a natural telescope etched into space-time itself. The result, a grainy smudge labeled Jade's GSE 13, a galaxy born just 300 million years after the Big Bang, its light stretched and dimmed by the expansion of the universe into infrared whispers Webb was designed to hear. What makes these images revolutionary isn't just their distance record, it's the chaos they've unleashed in cosmic archaeology. These early galaxies shouldn't exist, at least not in such abundance or maturity. According to dominant theories, the universe needed 500 million years to cool enough for gas to coalesce into stars, yet Webb found fully formed galaxies flickering to life shockingly early. Some glow with unexpected brightness, their stars packed tighter than modern models allow. Others sprawl with intricate structures, defying the notion that early galaxies were mere blobs of hot gas. It's as if we've opened a textbook on human evolution and found a Renaissance masterpiece in the chapter on cavemen. The secret lies in Webb's ability to dissect starlight like a cosmic prism. Every spectrum it captures carries chemical fingerprints, traces of oxygen, carbon, even water vapor, in galaxies that existed before these elements should have been widespread. One perplexing discovery, galaxies from the so-called cosmic dawn already contain dust, the gritty residue of dead stars. This suggests generations of stars lived, died, and recycled their material into new suns faster than anyone thought possible. The universe's infancy, it seems, was a frenzied nursery where stellar generations rose and fell in the blink of a cosmic eye. Beyond rewriting galactic history, Webb has turned its gaze to our cosmic backyard with equal brilliance. Its images of the Carina Nebula's cosmic cliffs reveal stellar nurseries where suns are born in violent splendor, their jets carving valleys in clouds of gas taller than our solar system. The telescope's study of exoplanet atmospheres like the scorching world WASP-96b detected water vapor and clouds in a sky where temperatures melt rock, proving even hellish worlds can hide clues about the chemistry of life. And then there's the haunting beauty of the Southern Ring Nebula, where a dying star's final breaths twist into delicate shells of gas, a preview of our sun's fate 5 billion years hence. Yet Webb's greatest gift might be the questions it forces us to confront. If galaxies matured too fast, did dark matter play a bigger role in their formation than we thought? Could some of these early galaxies actually be primordial black holes masquerading as starlight? Every new image is a riddle wrapped in stardust, challenging us to rethink not just how the universe evolved, but what it's truly made of. As the telescope peers ever deeper into the cosmic past, it's not just showing us where we came from, it's revealing how much we still have left to learn. The universe's first chapters, it turns out, are far stranger and more magnificent than our boldest theories dared to predict. Astrobiology flips our cosmic perspective inside out. What if Earth isn't the exception but the rule? Imagine a universe where life clings to hydrothermal vents on icy moons, blooms in the methane lakes of Titan, or even floats in the sulfuric acid clouds of Venus. This isn't science fiction anymore. When scientists found bacteria thriving in boiling Yellowstone geysers, worms wriggling in Antarctic ice, and microbes buried 2 miles deep in gold mines, places once considered sterile dead zones, the definition of habitable exploded. Suddenly, the icy shell of Jupiter's moon Europa, hiding a global ocean twice the volume of Earth's seas, became a prime hunting ground, or Saturn's Enceladus, where geysers spew water vapor and organic molecules into space like a cosmic sprinkler system. These aren't just curiosities, they're clues that life might be a cosmic inevitability, waiting for the right chemistry and a drop of liquid water to spark into existence. The tools of this search are as ingenious as the quest itself. On Mars, a Perseverance rover drills into ancient lake beds, sealing samples that might contain fossilized microbes, tiny time capsules from when the red planet flowed with rivers. The upcoming Europa Clipper will skim just 15 miles above that moon's frozen crust, using ice-penetrating radar to map its hidden seas. And then there's SETI, listening for radio whispers from distant civilizations, while new telescopes like James Webb sniff out biosignatures, molecules like oxygen or methane that could hint at alien photosynthesis in exoplanet atmospheres light years away. But astrobiology's real power lies in its humility. It forces us to confront how little we know about life's boundaries. Take Earth's shadow biosphere, a theorized ecosystems of organisms using biochemistry utterly alien to ours. What if life elsewhere runs on silicon instead of carbon, or breathes sulfur instead of oxygen? The Viking landers in the 1970s may have missed Martian microbes simply because they were designed to detect Earth-like metabolism. Future missions like Europe's Rosalind Franklin rover will search for molecular patterns that don't depend on our assumptions. The stakes couldn't be higher. Finding even a single microbe beyond Earth would answer humanity's oldest question: are we alone? But more profoundly, it would reveal whether life is a cosmic imperative, a natural outcome of universal laws, or a fluke confined to our pale blue dot. Every extremophile discovered in Earth's hellscapes, every organic molecule spotted in Saturn's rings, pushes us closer to a staggering possibility. Life might not just exist elsewhere. It could be everywhere, a silent symphony of biology humming across the galaxies, waiting for us to tune in. Machine learning has become astronomy's silent partner, working tirelessly behind the scenes to decode the universe's deepest secrets. Every night, telescopes like the Vera Rubin Observatory in Chile capture terabytes of data enough to fill thousands of hard drives with cosmic snapshots. No human team could possibly sift through it all, but artificial intelligence can. Neural networks trained on millions of galaxy images now spot gravitational lenses, those faint smears where distant light bends around massive objects with superhuman accuracy. They flag asteroids that might threaten Earth, track stellar flares erupting light years away, and even predict when a supernova might brighten our skies. It's as if we've given the cosmos a new set of eyes, ones that never blink, never tire, and see connections hidden in the noise. But the real revolution isn't just in observation, it's in simulation. Supercomputers running AI-driven models recreate the universe's birth, tracing how dark matter's invisible threads wove galaxies into existence. These digital universes, fine-tuned by machine learning, help astronomers test wild theories safely, like cosmic gardeners cultivating a million possible realities to see which one matches our own. Some programs, like Google's DeepMind, have even taught themselves to predict star movements more accurately than Newton's equations, hinting that AI might one day uncover physical laws we've missed for centuries. Yet for all its digital brilliance, astronomy's boldest dreams remain gloriously analog. Take Breakthrough Starshot, a plan to launch gram-sized probes toward Alpha Centauri at 20% the speed of light. Powered by Earth-based lasers pushing gossamer-thin light sails, these nanocraft could reach our nearest stellar neighbor in just 20 years, snapping photos as they zip past. Imagine tiny ambassadors smaller than a postage stamp, crossing 4.37 light-years to beam back images of alien worlds. The engineering hurdles are staggering: cosmic dust impacts, laser precision over interstellar distances, keeping electronics intact for decades, but the payoff would redefine humanity's place in the cosmos. What makes this moment unique is how these two frontiers, AI and interstellar exploration, are converging. Machine learning helps design lighter materials for space sails, models the best trajectories through interstellar plasma, and deciphers signals drowned in cosmic static. Meanwhile, every probe we send beyond the solar system, from Voyager to future Starshot missions, becomes a data point teaching AI more about the universe's true scale. The questions driving astronomy's next era are as old as civilization itself. Are we alone? What lies beyond the next star? But the tools we're crafting to answer them: self-taught algorithms and star-hopping nanocraft are unlike anything our ancestors could have imagined. As AI pours over ancient starlight and humanity prepares to reach for the stars, we're not just searching for answers, we're learning how to ask better questions. The universe, it seems, still has a few surprises left, and we're finally building the minds and machines to uncover them. From the first moment a human looked up and saw patterns in the stars, to the AI algorithms now scanning distant galaxies for signs we can't even comprehend, our relationship with the cosmos has been one of constant reinvention. Those ancient astronomers mapping constellations with nothing but sticks and shadows were laying the foundation for everything we know today. Not just about space, but about time, mathematics, and the very nature of reality. The same curiosity that led them to build Stonehenge and chart Venus now fuels our search for exoplanets and dark matter. It's astonishing to realize that when you check the time on your phone, you're using knowledge first gleaned from tracking celestial movements thousands of years ago. This journey hasn't just given us answers, it's transformed how we ask questions. Where our ancestors saw gods riding chariots across the sky, we see gravitational waves rippling through space-time. The myths that once explained eclipses and comets have evolved into equations predicting black hole collisions and quantum fluctuations. Yet some things remain unchanged. That same mixture of awe and determination that drove Babylonian scribes to record star positions on clay tablets now inspires teams analyzing data from the James Webb Space Telescope. The tools have changed, but the human drive to understand our place in the universe burns just as brightly. What's most remarkable is how each new discovery doesn't shrink the cosmos, but expands our sense of wonder. Finding water on Mars or organic molecules in distant nebulae doesn't make space feel smaller. It makes the possibilities feel infinite. We've gone from thinking Earth was the center of everything to realizing our galaxy is one among trillions, from fearing eclipses as omens to using them to test relativity. The universe keeps surprising us, revealing layers of complexity that humble even our most ambitious theories. Tonight, when you step outside and look up, you're participating in something extraordinary. You're continuing a conversation that began when the first human wondered why the stars move, and that will continue long after we're gone. The night sky is the one artifact all generations throughout history have shared. The same stars that guided ancient navigators still shine above us, connecting us to every person who ever looked up in wonder. And somewhere out there, in data we haven't yet analyzed or galaxies we haven't yet discovered, are the next revelations waiting to rewrite our story again. The cosmos isn't done with us yet. Keep looking.